So our next speaker is Professor Leni Bascones from CSIC in Madrid, and she's going to talk about correlations and introduction.
Okay, so well, first of all, I would like to start thanking the organizers for the kind invitation to be here. So what I'm going to do, in this first lecture, I'm going to give a generic introduction to correlation, in particular to what respect to the formation of local moments, which is and how the spectrum is modified. And this is something that I will use in the discussion of the correlations in two bilayer graphene tomorrow. And I think there are these type of concepts are going to appear in other talks. Well, so let me. Okay, so this is not working. So let me just start from the very basic. So we know that the way in which we think when we think on materials is we think on a bond structure. So early on we learn how the electrons see the average in the Bloch states. The electrons see the average potential of the solid. So we know in reality that the electrons also interact between themselves. So somehow our description, our spectrum should include these interactions. So in reality, when we think on the bonds and the ones that are calculated with techniques like density functional theory, the interactions between electrons had not been thrown away. So they have been introduced in some average way. So then we in this bond, so we get this average potential and the symmetry of the lattice. The great thing of having all this bond structure and this technique, this density functional theory technique, is that they can give predictions that can be very directly compared with experiments. In particular, for example, with herpes. You can see, really, you can compare bond structures calculated with density functional that works very, very well. So this is experiment, and this is theory. However, beyond this simple mean field description, electronic correlations can do many things. Of course, something that we all know is that electronic correlations can break symmetries. And they can break symmetries in many different ways. So here I have just plotted some cases in which there is mostly some, they break the symmetry of the lattice in some way, translational, rotational. There can be many different types of broken symmetry states, so they can break translational symmetry, rotational, it can be a spin, they can be charged, so on. And in fact, in many materials, we see many of these broken symmetry states. So in particular, in correlated materials, in the strongly correlated materials, the phase diagrams show a lot of phases which are competing or cooperating. You can see here there are some phase diagrams of different correlated materials. Here are the cuprates, here are the iron superconductors, organic superconductors, heavy fermions, twist bilayer. And what you see is a very a strong complexity, so many different phases, which appears in many cases just tuning some parameters. It can be pressure, it can be doping, it can be, well, in correlated materials, in wire materials, for example, it can be a magnetic field. You can see how we have all these states. However, you can also see that, so what it characterizes strongly correlated systems is that, so there are anomalies not only in these broken symmetry states, but also you can see that when we go up in temperatures, we also see anomalous behaviors. You see here, for example, the words bad metals, you see the words strange metals, and so on. In some cases, it's not written, but that does not mean that the observations don't deviate from the predictions from density functional theory. So there are many cases. So in general, so there are many systems in particular in the strongly correlated systems in which the normal states, and here I'm going to use the word normal in the sense of being above the transition temperature, has so the band picture does not work so well in many cases. And then this is going to give us states in which we are going to have correlations in metals. We are going to have situations in which a system that was expected to a metal can become an insulator even without breaking symmetries. We can have systems in which the bandwidth that we observe in an experiment it's much narrower than the one that is predicted by DMFT. And we can also have anomalous temperature dependence. And when we look at the spectrum, we can see some blurry spectrum. For example, this is an example that it was measured many years ago by Ming-Ji in an iron chalcogenide, and so somehow it's specifically this work about this work was about this, how this the anomalous temperature behavior was telling us about what was happening in the system. It was just not a thermal broadening. So this talk is going to be about the correlations here in this normal state. And I'm going to write normal state in quotations because it's not very normal. So it's anomalous. So I'm going to talk here about what type of effect appear overall in the spectrum of the systems. So let me start from the simplest again, from the Fermi gas. So let's first assume that we don't have interactions, okay? So what we know is that, in our band structure, we know that we have well-defined excitations. We have momentum K, charge E, and spin sigma. This is our band structure. So our excitations are follow the Fermi-Dirac distribution, and we have in metals we have the Fermi surface. Okay. So if we look at the spectral function, this spectral function is going to be a very important quantity in all the discussion. Is really what we see when we do an ARPES experiment. We add an electron or take out an electron, and we see the distribution of excitations that is created. So if we have a perfect band, which is what we have in a Fermi gas, we see that if we add an electron or take out with momentum K, here this is a hole because it's below the Fermi level, so our excitation is very well defined. It's a delta function, okay? And the excitation happens at the energy of the electron. So just having with this and with the Fermi-Dirac distribution, we can get predictions for the system, like how our specific heat is going to behave with temperature, is going to be linear, or the fact that, for example, the spin susceptibility is independent on temperature. So now, this is, in fact, the generic idea that we many times assume that it's working, but here I haven't used any interactions. Of course, the next level is that we know that Fermi liquid theory comes to tell us that, well, we have, so it's justified that we can use band structure to describe our systems. So here, we know that under the assumption of adiabaticity, we have a one-to-one correspondence between the electrons and excitations of the systems. So what it tells us is that we have fermionic excitations in our system, and that there is a one-to-one correspondence between the electrons and these elementary excitations. So these elementary excitations, these quasi-particles, follow a Fermi-Dirac distribution, okay? And so this tells us that a Fermi surface exists in our system. And so at zero temperature, we expect to have a step. Okay. So that we have this description that is what is going to be key to have a band structure working in our system. It's telling us that we can write our electron in terms of these excitations that we have, these fermionic excitations that we have called quasi-particles. And so because they are fermionic, so in the expansions that we do, we have to conserve, momentum, spin, and charge. And so you see this is the part. This is this one-to-one correspondence. To have this one-to-one correspondence, this quantity that we have here, that we call the quasi-particle weight, C is the quasi-particle weight, it has to be finite. Okay. So this quantity, it's a key concept because it's telling us how much of so how large is the overlap between our electron and our quasi-particle. And this part that you see here is the decay of the electron in the quasi-particles. When we think on the band structure in our system, in reality, and when we see them, in reality, what we see is the excitations of the quasi-particles. But the quasi-particles, in a Fermi gas, the electronic excitations are perfect eigenstates. The quasi-particles can decay. So fortunately, Pauli principle comes to rescue us and say, okay, well, quasi-particles are not eigenstates, but if we are at low temperatures and low energies, so our quasi-particles are going to be well-defined energies. So a well-defined excitation requires that the decay rate of our excitation is much smaller than the energy measured with respect to the Fermi level. And what we see is that thanks to the Pauli principle, so close to the Fermi energy, this scattering rate, so this decay of the excitation, it's going to be quadratic in energy and quadratic in temperature. So if the temperature and the energy are small enough, so this means that this quantity, this is omega, okay? This is the energy with respect to the Fermi surface. So this quantity, this excitation, it's going to be well-defined. And that is what it allows us to really have a band structure. We'll see now. Okay. So just with this, what we see is that our description, so the description of the system, is at low temperatures, it's going to have the same type of behavior that we saw in the Fermi gas. It just turns out that it's going to have some renormalized parameters. So, for example, the specific heat will be linear in temperature, spin susceptibility will not depend on temperature, but you see here this signs that is telling us that it's renormalized. Another important thing that it will appear at some point later in the symposium is that, well, in Fermi liquid, due to this decay proportional to a square of the temperature, so we expect that the resistivity is going to be T squared. on temperature. So this is the Fermi liquid, and this is the description in which, even if we don't realize that we are always assuming when we work with a band structure, and we take it for granted to be a good description of our system. So let me, and of course, as I say, we are going to have this quasi-particle band structure. Let me now go to show how our spectral function changes, which is what I will discuss a lot and go in more careful in the talk. In our Fermi gas, we said our band structure was perfect. So we have this, for a momentum k, we have a very well-defined excitation, perfectly defined. And so we have this delta function at the energy of the excitation. In the Fermi liquid, it's going to depend whether we are at the Fermi surface or away. At the Fermi surface, so the fact that we have quasi-particles is telling us that we are going to have this, we are going to have a peak, a well-defined peak. And this peak is going to be a delta function if we are at the Fermi level, because the quasi-particle does not decay. And it's going to have some width. It's going to be more kind of Lorentzian-like if we are away from the Fermi surface, okay? Now, you see here that besides this peak, we have this kind of broad continuum, okay? This is not in the Fermi gas. So this part that you see here is telling us about the decay of the electron in quasi-particle, quasi-Hall excitations, okay? So this is not well defined. So normally we call it this incoherent and the continuum, or the continuum. So the spectral weight of an electron is conserved. But now it's going to be split part in this quasi-particle peak and part in this continuum. So the quantity that is in this quasi-particle peak is going to be given by this quantity here, this quasi-particle weight. So this is giving us a measure of the correlation. It's telling us how much of our electron is really in this description that we normally use, this band. Okay, so one of the predictions that are very important from band structures is that we expect if, so in a case in which we don't have, we don't break the symmetry, so if we have an odd number of electrons, I'm going to here assume a spin degeneracy, the system is expected to be metallic. And the reason is clear, so our band is not completely filled. However, I think most of you have heard at some point that we can have insulators even when there are interactions. So imagine a case, I'm going to work with the Hubbard model. I think probably most of you have heard about it. So I'm going to assume a system in which I have one electron per side per atom. And then we have some hopping between these electrons. And then we have some repulsion when the two electrons are on the same side. Repulsion is U. So when electrons go from one side to another, at some points there is a double occupancy. So I'm going to consider a specific case in which there is one electron per side. So when when electrons go from one side to another, at some point there should be some double occupancy because we are at this specific filling. Now, if we have a double occupied site, then this costs energy. So when the electron is moving, it saves so we gain kinetic energy because of the hopping. When we have two electrons on the same side, we have to pay the cost of the interaction, this U. So this costs energy, okay? So this means that if U is much larger than the hopping, it's not going to be interesting for the system to be a metal. So what we have is a Mott insulator. This happens at large interaction as compared to the kinetic energy. And this happens specifically at this filling we will see now. Now, what I want to emphasize here is that, so when I have this specific filling, 1 electron per side, each of our electron is going to be occupying a side, and the charges, so fluctuations are going to be suppressed. The transport is going to be suppressed, but you can see that I haven't used any argument with that is in which I am breaking the symmetry. So somehow the Mott insulator does not need to break any symmetry by itself. It's the definition that we are not breaking a symmetry. So I want to emphasize this because many people, because in the Hubbard model it's quite often, and also in the insulating state, it's very often we have magnetic ordering. So many people confuses the Mott insulator with an antiferromagnetic insulator, but that's not the origin. Okay, so the origin of the insulating behavior is the suppression of the charge fluctuations. Later we will see that we form local moments too. You can see, in fact, here a case in which you see that when we rise, so here we are in an antiferromagnetic insulating state. This is an organic compound. We increase the temperature, and the Mott insulator remains. Okay. Okay. So normally we are here in this Hubbard model. And in general, the bandwidth, it's giving us information. So we are going to, on the kinetic energy for this, for our single orbital. And so somehow narrow bands are going to have, in general, a smaller kinetic energy and are going to be more sensitive to interactions. Okay, so far we have been at this specific filling, this half filling. Now, imagine that we change the filling, and we have, for example, created, so we have, the filling is smaller than half filling, than 1 per side. So if now you can see that if an electron wants to move, if there are empty places, the electron can move. And so the system will be metallic, okay? So the insulating behavior will be only at this specific half filling. In reality, in multi-orbital Hubbard models, it can also be at integer filling per site. Now, being metallic, that does not mean that the system is not correlated. So, in fact, when the electrons are moving, they can move because there are these empty sites, but the electrons are going to they will try to avoid the configurations in which there is already an electron. So it's not that the electron does not feel so the electrons feel this cost in energy. So the electrons don't want to go to the sites in which there is already an electron because that costs energy. So this is going to have an impact on the spectrum of the system. This happens for the case in which we are away from Hall filling, but this also happens in the case in which we are at integer filling but below the Mott transition. So somehow the interactions are not so strong to kill the transport, but somehow whenever the electrons move, they are going to do it in a way in which they will try to have the minimum number of double occupancies in the system, or of double occupied sites in the system. So most of what I'm going to do now is I'm going to try to characterize these correlated states. Okay, this correlated metallic state. So imagine that we assume, so if we are in the Fermi gas, so whenever an electron moves from one side to another, so we have our band structure in K. In real space, we can think, so somehow is that an electron can go to another side, and it does not care if there is, as far as the spin is different, if there is already one electron in that site. So the occupancy of each site with 0, 1, so the spin up, the spin down, or the double occupancy are the same. It's 0.25 for each of these possibilities. Now, we are saying that it seems that the electron will like to avoid this double occupancy. So a way in which we can try to characterize this is to say, okay, let's assume a wave function. So this is the Guth-Wheeler wave function, in which, so we start from the Fermi C, from this uncorrelated metallic state, the one that we will have for a Fermi gas. But then let's try to kill this, let's try to suppress the double occupancies, okay? And here, the amount of double occupants, the way in which we are going to suppress that is with variational parameters, okay? So if eta is 0, so we are suppressing all the double occupancies. If eta is 1, we are in a Fermi C. So, well, one can do this. This is a way of doing this in a simple approximation in the what is called in some mean field way. You can see that if we allow the system to avoid these double occupancies, so it will choose to suppress them, and there will be less and less. These are the number of double occupancies, less and less double occupancies as we increase the interaction. So when this is happening, so you can see this is the energy per particle. This is what happens if we are just in the Fermi seat, we don't suppress the double occupancy. So, and you see that suppressing double occupancy is decreasing the energy of each particle. You see that they are below. Okay? So one thing is that the system managed to be a metal for larger interactions. So here, this is here is the Mott transition, because here is not interesting anymore for the system to have transport. And here you see that the system managed to be a metal for a larger range of interactions. Okay, so somehow this suppression has to influence the spectrum of the system. You can see now here how the system decreases the interaction. So this is what I have shown you before. This is the total energy. Now here, what you have in green and yellow, this is the interaction energy. In green, you have the interaction energy in the uncorrelated state. And you see here how in the correlated state, the interaction energy has decreased. This is what we expected, okay? We decrease the number of double occupied sites, and so the interaction energy decreases. Fine, we expected that. Now, so we see, and here what we have is the kinetic energy. That I forgot to put it. But so you see here, this is the kinetic energy in the uncorrelated state, and here is in the correlated state. So somehow the gain of kinetic energy in the correlated state is smaller. So we have paid the price. So we decrease the interaction energy, but because we are avoiding these many possible configurations, sometimes the electron cannot go to some other neighboring site. So we are paying a price of our kinetic energy. So then what we are going to have then, because we reduce the kinetic energy, effectively in our correlated state, what we can expect is that our bandwidth, so our bandwidth is giving us an idea of the kinetic energy. So correlations are going to reduce this the bandwidth of the so the bandwidth of the quasi-particles is going to be smaller than the one that we will expect without taking into account these correlations. So imagine this is the density of states. So this is just the integral to all the K momentum of the band structure. So we now start increasing U, and so our density of states will become narrower. Narrower until at some interaction, if we are in at half integer, at half filling, it will disappear in what we call the Brinkman-Rice transition of the Mott, description of the Mott transition. So this is a kind of Fermi liquid approach in which what we just see somehow is how the mass of our electrons have become larger, and this can be seen in ARPES, for example. So it's very common to characterize the strength of the correlations by how much how much larger is so how much narrower is the band as compared to the prediction from density functional theory. Okay, so you can see here as a function of interactions and filling. So this is how much the band becomes, so how narrow it is as compared to the, and this is the, in fact, this narrowing gives the quasi-particle weight. And you can see how at half filling, really, the quasi-particle weight vanishes in the Mott insulator. So the band has become completely narrow. So this is black. But you can see is how there is a region, large regions of filling and also interaction in which the system is not in the Mott state, but this effect are very prominent. So here, when we are in the violet or red, so is the correlations are important. Okay, so we cannot just not forget about them. And what you can see, and this is for the single orbital case, later I will show how this can be a bit different. You can see how, if we look, before I told you that Mott was about suppressing charge fluctuations. So here we are looking at charge fluctuations. Okay, so this is how the charge, so this is the charge per site, square minus the average. So this quantity is telling us how much the charge is changing from one side. And you can see how these charge fluctuations follow this, the interactions and follow. So how, as we approach the mode transition, these are suppressed. But you can see here again that even here we are in a metallic state. So charge fluctuations have been considerably suppressed. At the same time, I have told you that we create local moments. And you can see here, this quantity is telling us that when we form a local moment in our system, many times when we talk about, okay, this is a moment, and we just put an arrow, but we don't think reality many times what we are doing. And so you can see how this really goes to when we approach mode. So here is where our magnetic moment forms. So here we are forming a moment, which means that or we are going to have one electron with a spin up or with a spin down. I am not ordering them. So what I'm creating just is a paramagnetic system, okay? So it just say that we are not going to have neither empty states, neither double occupied states. Okay, so far we have seen that we expect that the bandwidth of our system becomes narrower. And we have seen that we suppress the charge fluctuations and we form the local moments. However, and so when we have seen this narrower band, in reality we are talking about this quasi-particle peak. However, we still have not seen anything of this continuum. So let's now approach the problem from a completely opposite point of view. Let's now start from the atomic limit. So let's now start from not having kinetic energy, but just having interaction. Okay. So if we are in an atom, if we just have the interaction, if here it does not cause energy is 0. But if we have 2 electrons in our system, the energy is U of that state is U. So what you can see is that, well, this type of a spectrum is completely non-band structure-like. So it's really completely non-rigid band shift. So I'm just going to put this in a different way. So our density of state, it will be 2 peak. I'm assuming half filling here. So our chemical potential is here. And so these are the peak which is associated, it will be associated to single occupancy, and this is the one associated to double occupancy. So our spectrum has been split in 2 peaks, which are what we call the Hubbard bands. So if we now start switching on the interactions, this peak become a bit wider until they even can close the gap. But here, you see here, we don't have a quasi-particle peak. Okay, so this is everything, it's very broad. And so somehow, what we have done is we have reached to 2 completely complementary, but let's say opposite ways to looking at what's happening here. So here, starting from the metal, we have seen that our quasi-particle band becomes narrower. Here, we just have all these parties incoherent. So this looks like as if we will expect that our spectrum is something like this if we put the 2 descriptions together. So in fact, these 2 descriptions that I have done are very simplistic. And if we want to do better, we have to go to some advanced numerics. So this is, for example, what one can do with dynamical mean field theory. So we can imagine that we start from a very weakly correlated band in which what we have is, well, we just essentially see the quasi-particle part. Okay, it's our spectrum. This is the density of a state. Somehow, and this is the opposite limit. This is an interaction. This is half-L again, and this is a system in which we are already in the Mott insulating state. Okay, so what you can see is that as the interaction increases, what we see is this quasi-particle peak becomes narrower, and at the same time we are start expelling a spectral weight to higher energies. As larger are the interactions, this is higher, so they have higher and higher spectral weight, and this part becomes narrower and narrower. You can see that these Hubbard bands are already well developed in the metal, okay? So it's not, so sometimes we thinking, or I have a band structure that can even have some symmetry breaking or something like that, but I think on a perfect band structure, or I think on a Mott insulator in which I just put some arrows to signal that, and which has Hubbard bands. But what you can see is that this is not always such an easy binary choice. So the metals have, in many cases, strong signatures of the correlations, and in particular, they can have a lot of their spectral weight in the incoherent part. So you can see here, it's only when we have said before that the quasi-particle peak, so how much our band structure works so how much of our electron is in the quasi-particle state is given by the spectral weight that this is in this quasi-particle peak. And as you see that when we approach Mott, this becomes very small. The Mott transition happens when this quasi-particle peak disappears. So you can see a bit here. It's probably easier to see in the bands. So this is the band that we normally have in mind. This is the non-interacting band. It's perfectly well-defined band. So these are real eigenstate. Okay. This is a Mott insulator in which this is incoherent. We have split our spectrum. What you can see is that the way in which this non-interacting to Mott insulating evolution, you see how we are spelling. You see here how we are start spelling spectral weight. We start having blurred spectrum, okay? And we send more and more of this spectrum. You see here also that this band is becoming narrower. This here in dashed line is the non-interacting band. And there is more and more of this spectral weight shifted to higher energies as we increase the interaction. So this is what I referred before. This was our band. This is our quasi-particle peak. And all this blurred thing is all this continuum. So this is the amount of the electronic excitation, which is not in the quasi-particle state. Okay, so let me, before continuing, I don't know how much time probably. So let me reorganize things. So we have seen, and this is the main message, is how the interactions can produce a very strong reorganization of the spectral weight. This appears in when we look at the spectrum in ARPES, when we look at the density of states in an STM spectrum. And this happens even in the normal state above symmetry breaking transition, above any ordering transition. So this is the physics. There can be many reasons. The physics that I discuss here is associated to the formation of local moments. Now, under certain conditions, this can even lead to a metal insulator transition, which is the Mott transition. And I want to emphasize how the Mott transition is associated to suppressing charge fluctuations and forming local moments, but not necessarily ordering them. It happens very often that magnetic moments are ordered, but it's not mandatory. So, and of course, this also give us reorganization not just in the insulator, but also in the correlated metals. So something important is that to see this, we need certain techniques that I'm able to address. Now, another thing that I have mentioned, and we will see a bit more, is this density of states. It's going and how this spectral reorganization takes place is very sensitive to the filling, to the electronic filling. We have seen already that this can even determine whether the system is really has the Mott transition or not. And it's also very sensitive to temperature. And another thing is that important thing that I will mention a bit too is that so while this is the generic description, different materials are not going to be so simple as a single orbital Hubbard model, and they can have very important differences in how they manifest these local interactions. Do I still have some time, or 2 minutes? Okay. So the very first thing, why do we care on this? Okay. Well, the very first thing is if this produces, as I have said, this produces manifestation. So it has manifestation that we can see in an experiment, in an ARPES experiment, in an STM experiment, and in reality, because we are affecting directly this spectrum, it's going to affect probably any property that we can measure, or many properties that we can measure is going to be there. So in many cases, generically, or to some extent, the effect that we have in the normal state, if we break the symmetry, so a lot of this reorganization of the spectral weight, it's going to remain also in the is going to remain in the broken symmetry state below a transition temperature. So if we see, imagine that you just see this spectrum in an STM, for example, or this in ARPES, somehow something. Sometimes, if you are not aware that this physics is there, you may think that this is associated to some broken symmetry, and you cannot maybe you don't know that this is really a property of the normal state. So you can be confused when you try to interpret experiments. Another thing is that knowing how correlated is a system can be key to try to understand how is the type of broken symmetries that can happen in a system. Imagine this case, for example, a square lattice, just hopping to nearest neighbor. So if we are in weak interactions, so we have a really well-defined Fermi surface, and our system is better defined by this Fermi surface, we really have this type of Fermi surface with a lot of nesting. So we say, okay, this is going to favor antiferromagnetism. I'm not going to enter into that, but the question is, this here, the Neal temperature will increase when U increases. If we are in the case in which interactions are large and our system is more dominated by the incoherent part, the system, it's better defined but, by local moments. And so then the Neal temperature will go like super exchange, like T squared over U. So in this case, the Neal temperature will decrease when U increases. So somehow, knowing that this physics is there, it can make that we are able to distinguish whether we expect that the Neal temperature will increase or will decrease. In this case, both the weak correlated and strong correlated limits give the same type of magnetic state, but there are cases in which in the two limits we can favor even different symmetry breakings. Okay, so I'm going to stop here.
With the Gutzwiller wave function. Yeah, there it was.
This?
Yeah,
This one?
a few slides forward, please. More.
Okay, this is Levy spin. This is not exactly what Bill, but it's similar description, yes.
Yeah, I was about to ask the details of this calculation. What kind of density of states do you assume, like a step function or?
Okay, so this is, you start in this case, so this for this specific one, here we started with square lattice so square lattice, but you have similar behavior for other density of states. So in the calculation here, this is one of these slave particle calculations in which you introduce extra degrees of freedom, and then later you do you put some variational parameters because to reduce you have introduced extra states that are non-physical, and you try to eliminate them.
So 2D square lattice.
Okay, yeah. So in this case, so it's the dispersion for a 2D square lattice. But so here, okay, something that I have not said just because I haven't emphasized. So this is, we are assuming that all the renormalization does not depend on momentum. So it's a single side description. In that case, the main, what it interests mostly in the calculation really is the density of states that you have. So somehow in low dimension, the K-space, it's important. That So you have in mind something specific?
No, that answers the question. Thank you.
Okay. Yeah. Yes.
Thank you. So if you go to the slide where you were increasing the interaction strengths and going to the Mott transition, the spectral weight shifting to
the three-peak structure?
Yeah.
This one?
Yes, exactly.
Okay.
So in like 1.25 and 1.5 and the Hubbard bands, we see some sub-peak. There is more peaks to it. Do they have any physical significance, or like, can I interpret them physically in any way?
Well, because this is for specific beta lattice, but I don't think that there is, because even in this case, so somehow so one thing is that this is of 96. Also, this was a very, so this is, I think is a way of solving the DMFT that is, it's very, at that time it's very basic. So, well, just keep the idea of the three peaks. So no, these small peaks, I don't think they have anything. It's a bit the way in which this is throwing the.
So if I do a more advanced DMFT, these peaks do not show up, or
these small peaks. So I don't think they are showing. So normally it's more like generic, but it depends a bit on the system and how is the dispersion and all that. Yeah.
I see. Thank you.
So I don't have them in mind at least, and
it's okay. Thanks.
If this calculation is done on beta lattice, how can you distinguish the quasi-particle peak, like on the Fermi surface, from some kind of broadened resonance on the Fermi surface? I mean, yeah.
Normally, if you, for example, do ARPES, so if it's the quasi-particle, you normally see well the dispersion. So somehow you have the, normally, I don't have anyone here. I guess that Mingji probably will put at some point in her talk something. So you normally see different spectrum that you measure as a function of momentum. And then you see if it's the quasi-particle peak first is, well, normally you see how it's a kind of a bit sharper peak. And then you see a bit how it it depends. So how the position of this peak changes in momentum in a kind of following a dispersion of a band. What you will see a band. But I can tell you that sometimes, for example, in the cuprates, there are many spectrum in which you couldn't say, okay, it's what's this? it's not always obvious. Sometimes it's so broad in it that you really cannot say that. Yeah. Okay, this is so. One thing is this is the density of a state.
As far as I understand, the nature of the effect is the sudden breakdown of the Fermi liquid, right? When the Z becomes 0.
Well, yeah, but this is here. Okay, sorry, I was not understanding. So you don't. So you see?
No, but I don't see a Z here. This is like density of states. I mean, the Z has a K label, momentum.
Okay, yeah, no, this is this is the density of states, and for the beta lattice is what you can have. For the beta lattice, you don't have the band structure.
The nature of effect is just the breakdown of this very narrow peak in the middle of the density.
The breakdown of the Fermi liquid in beta lattice.
I mean, is there a Fermi liquid in beta lattice?
Okay, so this is okay. So if you think, for example, from the point of view of the technical thing, you get the green function, and then what you look is how is the behavior of the self energy, and from the self energy you can see that. So one thing is in the real part of the self energy, you have a linear dependence on frequency close to zero frequency, and you can. So this is normally what is giving you. So this the slope of that. Of that dependence gives you the quasi-particle weight. So you can see when this goes to 0. Normally, for these things, you do what is called normally a quasi-particle analysis. Yeah.
Thank you. Hello. Thank you for the nice lecture. I'm trying to think about examples of formation of local moments beyond spin, for example. And I'm wondering if you can say a bit more about how common it is, for example, in bilayer systems to form, use the layer pseudospin and have local moments in.
So okay, so in a bilayer, so somehow here I have really gone to the case in which you have a very okay, let's say. So you want a bilayer that is also coupled. In the case, for example, is you will go. Okay, so just don't think on graphene at this moment, okay? But in principle, imagine a system in which what we have is you have two different type of electrons. Let's say, okay. So you may have more than one electron. So more than one side. You can have two different type of things. One I was planning to mention, I didn't have time, is you can have more than 2 electrons per side. And so then you will have a kind of multi-orbital model. If you have different, so you have your electrons are on different sides, this is a bit more complex in the sense that with the type of techniques that I have told you, so you only see the effect of the correlations on the same side. That is because of the techniques that I have told you. But in principle, let's say, for example, if you have something also like valleys or something, you can also have a similar behavior than the one that I have mentioned. This case, in fact, that I put here, no, not here. It was for a 2, I didn't tell you, but it was for a 2 orbital system. But this is a specific system in which you have a moire, so it's not, and this is, but so this is for you have 2 orbital here that in reality are the valleys. So that, and so somehow is, I don't don't know if I'm answering your question.
Yeah, I think that's the direction in which I was thinking. But can you think of formation of local moments in the same way in this case, for example?
I'm going to be conservative. I will tell you yes, but specifically you have to be careful on thinking on which is exactly the system, because in some system it may be yes, in some other system it may be no. Okay, so.
Yeah. Thank you.
I think we should go to the coffee break, and there you can keep discussing with Leni. Thank you.